You're listening to the FQXi podcast. Today,
Go quantum!
we begin the countdown of this year's biggest stories in physics.
What they did in this experiment, is they simulated one of these traversable wormholes on a quantum computer.
As chosen by quantum physicist Ian Durham.
And so, did you actually then create this traversable wormhole with the qubits that are processing the data doing the simulation? And I think that's sort of the deeper philosophical issue here.
I'm Zeeya Merali. Welcome to the End of Year podcast series from the Foundational Questions Institute. As usual for the holiday season, I am joined by FQXi member and quantum physicist Ian Durham of St Anselm College in New Hampshire. Ian, of course, spends the year diligently monitoring the headlines for the biggest, the best, and the most notorious advances and claims in physics. We begin, as always, with a discussion of some of the highlights that didn't quite make Ian's top 5 list. Hello, Ian.
Thank you, Zeeya. It's a pleasure. I have no idea how many of these we've done now. This has got to be 6 or 7 years now. Something
More than that.
Wow. Okay.
And I think, just to interrupt you there, you have mentioned some things that are relevant to this list in the past, and you have a very loyal listener base, and they might be checking for consistency to see whether some of the promises you've made in the past will actually be held up now.
Uh-oh.
We'll get to that when we get to that.
Okay.
We're recording this in December 2022. I want to just say thank you to all of these physicists who keep making announcements in December. I appreciate that you're doing this just to get onto Ian's list, but you don't have to leave everything to the end of the year. There's been a lot of excitement in the past few weeks. It just forces us to record later and later in the year. Ian, before I sort of hand over to you, I think there are two things that people know that we're going to be talking about, or can make a very good guess that we're going to be talking about. So I'll just flag those up now. One is going to be fusion, and the other is going to be wormholes created in the lab. And I will let you take it away, Ian.
We'll get right down to it. So, as usual, I have a nice long list with lots of runners-up, and of course, as always, there will be controversy, or as Zeeya likes to say the word so that my friend Carl can make fun of me.
Controversy.
Yeah, see, there you go.
Controversy, that's how you pronounce the word. There's nothing wrong with that.
I should just point out to Carl, because he's going to listen to this, that it's the English who invented the language, not the Americans. Okay, I'm just going to start quickly by mentioning that, of course, this year's Nobel Prize was a big deal for FQXi. Anton Zeilinger is an FQXi member. I know Anton well. I know, in fact, his group in Vienna. I've been there. I was just there this summer. I mean, I wasn't there to do work. I was there. I had breakfast with Czaslaw Bruckner, who works in Anton's group.
So we should mention what the Nobel Prize in Physics was actually given for. The Nobel Prize in Physics 2022 was awarded jointly to Alain Aspect, John F. Clauser and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So entanglement is something we talk about a lot on this podcast, but it's that quantum phenomenon where multiple particles can become linked, where they are prepared in such a way that their properties are correlated, so that when you measure one and read the result, you instantly know what the result would be if you measure the corresponding property of its partner.
So in the 60s, John Bell sort of attacked the EPR problem, the famous Einstein-Podolsky-Rosen thought experiment problem, about entangling particles. He came up with an inequality that could be tested. And Clauser did some experiments in the early 70s. Alain Aspect in 81, 82, I think, did an experiment that I think really convinced a lot of people that, wow, okay, this entanglement thing is real. Now, entanglement is kind of routine. Espay did it in a photonic laser experiment, and I essentially do Espay's experiment every year with my students, and it involves entangling photons. It's a cool experiment.
And what did Anton Zeilinger do that sort of added to that?
Anton has, he's got this setup in Las Palmas. It's on the Canary Islands. So keeping photons entangled is tricky because when you've got photons flying around in the air and stuff, they bump into things. And when you bump into things, it's an interaction. And so it breaks entanglement. Things like gravity can degrade entanglement, all sorts of things. So it's hard to keep these particles entangled for long periods. And Anton has this setup where he's got these lasers shooting from these giant telescope things in the Canary Islands, Las Palmas, and he's kept photons entangled for well over 100 kilometers. They can be apart and still remain entangled with one another. Now, I think the Chinese recently broke that record, but that's just one of many amazing foundational experiments in entanglement that Anton has done. Anton's a really interesting guy, too, because Anton is one of these people that sort of works both in theory and experiment, and I've always admired him for that.
Yeah, no, on the podcast page, fqxi.org/community/podcast, I will put a link that you reminded me of to an article that I wrote some years back about the quantum space race between Anton Zeilinger and the Chinese group, which is led by Jianwei Pan, who is Anton's former student. And so they have a little bit of a rivalry going there, but also an immense friendship. And as you say, they just keep breaking records. And there's some lovely photos as well showing these massive telescopes that you mentioned, I think in Tenerife or wherever they are, and sort of photons flying through the night sky. So, yep, honourable mention, or I guess just a special mention to the Nobel Prize Committee for getting it right and awarding an FQXi member a Nobel Prize. I think the Breakthrough Prize this year also went to a few FQXi members, but also for sort of that field of quantum information. David Deutsch, Peter Shaw, Charlie Bennett, and Gilles Brassard. So it's been a good year in terms of recognizing work that I think the community has appreciated for a very long time.
Yeah. Go quantum.
It's sort of an honourable mention, but not really, because it's not like the work was done this year. And we're all about sort of breakthroughs that were made in 2022. So, now, as is traditional, Ian, what hasn't made your list, but could have?
Well, we should probably start by talking about what everyone probably tuned in to hear, and that's wormholes.
Wormholes, created in the lab, created in a quantum computer.
Yes, or not.
Yes, no.
Okay, so there's this big story that some wormholes were created on a quantum computer, and so the news got broadcast that a wormhole was created in a lab.
And this is because, very crudely put, and we will get to the subtleties and the nuances and more of the details later, but crudely put, within this quantum computer there was some special manipulation of its qubits, some entanglement, and that entanglement can allow information to be teleported, and that particular quantum process can be related by theory to the passage of information through a wormhole or a tunnel in space-time.
Now, I'll repeat what FQXi member Scott Aronson said in, I think, a New York Times article or something like that it's no more a wormhole than what you would create with a pen and paper. What they did is they simulated a wormhole on a quantum computer.
So wait a second, before I'm going to get into the details of what they actually did, I just want to say I am quite excited about talking about this story, and for a few different reasons. You sort of started off and you're scoffing a little bit about the big claims and the big headlines that came out about a wormhole having been created, and you brought up Scott Aronson's comment there to the New York Times. I do really want to talk about this for a few different reasons. So one is we're going to explain, and we might take a bit of a while to explain why a wormhole hasn't been created, but something interesting has happened in terms of physics. Like the physics behind it is very interesting. It's got quite a long history, and quite a lot of FQXi members are involved. I've written about this in the past, going back quite a long way, this sort of connection. And George Musser, he's an FQXi member, formerly of Scientific American, one of the best science writers out there, has written a 60-page review for FQXi and the John Templeton Foundation about the topic of emergence, which deals very, very much with this. And so if you really, really, really want to get all the background, I'm going to put a link on the podcast page, fqxi.org/community/podcast, to George's 60-page review, which is very accessible. It's written for the public, and to a story that I wrote about it and some that I've written for Nature in the past about some of these issues that we're going to get into. So the physics of what's happened and what was done is interesting, but I think there are a couple of other reasons why this is interesting. One is, what exactly were the claims that were made in the paper in Nature about it, in the news and views in Nature about it, and then in the press about it? And, how did that message perhaps get changed? Or maybe it didn't get changed. And then an even kind of deeper philosophical question of when you say whether or not something has been simulated versus when it has been created. Because it may be that most people now are kind of saying, no, this was a simulation. But it does raise very interesting questions about how these experiments might go in the future and where you kind of draw the line between something being simulated and something being created when we're getting into what we're about to speak about, which is duality between two different systems. So you were talking about quantum entanglement, which is a very quantum thing that everybody that studies quantum physics gets to hear about. And you're talking about wormholes, which is much more a general relativity thing. It's a tunnel in space-time. And as fans of the FQXi website will know, physicists have been struggling for many years to get quantum mechanics and general relativity together in a theory. And this particular piece of history in the history of theoretical physics does connect them. And another reason it's very exciting, which we will get to, is that this is all based on a theory called the SYK model. And S in the SYK model is an FQXi member, Subir Sachdev, and he's a condensed matter theorist. And so, one aspect of this that I don't think came out very much in the press was that all of this kind of had its origins, not from sort of theorists thinking about general relativity or thinking about quantum mechanics, but about a theorist who was thinking about how to describe matter that is created in the laboratory for, very practical purposes and some big mysteries that were happening around there. He was actually inspired by trying to solve the mystery of high temperature superconductivity. So I don't know if you want to talk about that or I want to talk about that, but somewhere we should talk about that because condensed matter doesn't get enough of it just doesn't get in the papers as much as it should.
Let me just start by saying that condensed matter theory does make my final five.
Ah, spoiler.
Yes. So we will come back to condensed matter. Yeah, so what they did is they simulated a wormhole on a quantum computer. And so it was a traversable wormhole. So there are these types of wormholes known as traversable wormholes, which have been theorized for many years. And they showed that you can send information down one of these traversable wormholes. But again, it was a simulation on a quantum computer. Now, it has long been supposed by many people that there is a connection between the concept of a wormhole and the concept of entanglement, which we just spoke about in regards to the Nobel Prize. So what are entangled particles? Well, entangled particles have this funny behavior. They seem to be correlated in a way that appears as if it would sort of be instantaneous. So like when you make a measurement on one and it comes out a particular value, the other value is instantaneously determined. Now, you can show, it's actually a fairly easy math problem to show that you can't actually use this in any way to transmit information. However, entanglement's still weird and it still allows us to do some really bizarre things. And so people have long thought that there was possibly some connection between entanglement and wormholes. In fact, the thought had long occurred to me even before I knew what any of this stuff was, back when I was just a mere student. I thought, oh, gee, It seems like this entanglement stuff, what if maybe it's because there's a wormhole, that the quote instantaneous communication was a wormhole kind of thing? Some of this is based on the ADS CFT duality. So ADS stands for Antidecitter, which is a type of space-time, solution to Einstein's equations kind of thing. And CFT stands for conformal field theory. A lot of people in condensed matter theory sort of work in this area.
And now this is going back to this conjecture that was made in the 1990s by another FQXi member, Juan Maldacena. So ADS is, like you say, the space-time part. Mm-hmm. It's describing a kind of space. Very crucially, we should say it's not the space we actually live in this universe. We live in a Disitter space.
Yes.
An Antidecitter space is quite different. It's a space with a boundary, and it has very different properties from our universe. But it is something that theoretical physicists have been studying for a long time because it's just perhaps easier to describe. And then the CFT part, which is the other part of that duality, is the quantum part.
So the conjecture is that there is a link between Antidisitter space and conformal field theory. So the ADS CFT, sometimes called correspondence. It's popular in string theory. It's this idea that there are sort of different theories that seem like they're not even really related, but that when you realize you kind of put the two together, you're like, oh, maybe they actually are. It came out, Juan Maldacena's work. One thing, that I'm aware of, there is no formal mathematical proof of the equivalence of these two.
No, I don't think there is, no. No, I was going to say, so on the website in that report and also in the article that I'll link to, you'll find some very nice graphics that we created to help people visualize what's going on here. And, the string theorists that work on this correspondence, they very often talk about this kind of soup can picture. So you imagine, a tin of soup, and that is your ADS space. And inside the soup can, you can imagine your black holes and your wormholes and gravity inside the bulk, so inside the soup. And then living on the exterior, the boundary of the can, you get your sort of quantum particles, and they are governed by this CFT. And so you can sort of find this equivalence between equations affecting the behavior of the black holes and the strings and the wormholes inside the bulk, and that is equivalent to equations on the boundary. And I'm making a bit of a meal of this and explaining it quite a lot because I think it's going to come up as we go on. Because when you talk to people who work on this, they have different interpretations of what that means. And one of the simplest is it's just a mathematical trick. It means that, I want to find out how a wormhole in the bulk behaves. I can't do the equations, they're quite hard, but I can map it to a system on the boundary that is simpler mathematically. I can do the calculation there, and I can work out the answer about what I wanted to know about the wormhole in the bulk. And that's sort of one sort of way of thinking about this correspondence. And then you have other people that are like, this shows that there's this very deep connection between gravity and these objects in space-time inside the bulk and quantum theory and the particles on the boundary. And that's like a really deep identification to the point that you can say that, gravity and some of these gravitational effects are identical to these quantum effects, and maybe one is emerging from the other. So there is some room for interpretation here.
Yes. I long sort of thought, why do we spend so much time on Antidecitter Space? Because we don't live in Antidecitter Space.
I will say one thing about why they study ADS, the Antidecitter Space. And this was something that was said to me by Ahmed Almieri, basically on an article I was writing about this a while ago, earlier this year. And I'd sort of said to him, what is even the point of studying the behavior of, what he was doing, which was black holes and wormholes in an ADS space if we don't live in an ADS space? And he said, it's like studying the properties of a tiger in a cage. You want to know how a tiger behaves. It won't behave in a cage exactly as it does in the wild, but what you're interested in is the tiger, not the cage, and you will be able to learn something useful. So that is why they look at these ADS spaces.
Yep. I think this is a good place to sort of connect to this claim that came out recently. So the wormhole part, sort of can connect to that gravity, not so it's type 2 supergravity. And then the entanglement part, of course, can be described by the conformal field theory. So if you believe in this, if you believe in the ADS CFT correspondence, and you believe that entanglement really is related to the concept of a wormhole, then you would think that pretty much any time you get entanglement, that there are wormholes popping up here and there in the universe, whatever. But they're not necessarily all traversable, right? So there's this class of wormholes that is traversable wormholes, where you can actually send something actually down it. You know, if you saw the movie Interstellar, that you could fly a spaceship right through it. What they did in this experiment, what they did is they simulated one of these traversable wormholes on a quantum computer. Now, quantum computers make use of entanglement. So the qubits are entangled. So the question is, this is a sort of a deep philosophical question about how things work. So let's say you model something on a regular computer, modeling it with some gates and some voltages and things like that. You know, you could say, well, can I trace, let's say, right now I'm running Google Chrome because this recording software works in Google Chrome. So could I trace Google Chrome back to specific bits and voltages and things in the microprocessor on my computer? And of course, most computer scientists and computer engineers would probably say no. But the idea would be then, if you could, then you could say, okay, then if I simulate a wormhole on a quantum computer, what I have to do is a modeling entanglement. When one assumes that by modeling entanglement on a quantum computer, you've probably actually created real entanglement. I mean, quantum computers function on entanglement. There's some entanglement going on in the processor, they quote processor, right? So then the question is did that model that you just created, that simulated and that spit out stuff on your screen, can you tie that directly to an actual entanglement thing that happened inside that machine? And so did you actually then create this traversable wormhole with the qubits that are processing the data doing the simulation? And I think that's sort of the deeper philosophical issue here. So Scott Aronson would say, no, you can't connect what's going on at the processor level, even at a quantum computer, to what is going on at the larger level of, the data level. And I'm not a computer scientist, so I know there are different names for the different levels that you talk about in computers. You've got stuff going on at the processor level, which is the very physical level, and gates and switches and voltages and things, and then you're going all the way up through machine language and blah 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 blah, all the way up until eventually it comes out on like a computer screen or a readout or something like that. Scott says you can't necessarily make that connection, the connection between, so this concept of emergence, what happens at that most fundamental level of a computing device versus the readout of that device, and how much of a connection can you make between those two? And I think that's where things sort of took on a life of their own with this. I personally am of the opinion that this result, while very good and very interesting and very important, did not create an actual wormhole. Unless, and again, the only caveat to this is unless if entanglement really is a wormhole, like if there are wormholes just wherever you have entanglement, well then there are little mini wormholes all over the place all the time, constantly, because there's entanglement everywhere. But I don't think there's any evidence that that actually physically occurred in the processor. Now, I don't think there's any evidence it didn't occur either. It's very well possible that in the processor of this machine, there was a traversable wormhole that was briefly created. But it's also possible that there was never that, and that it's just this simulation that came out on the screen, just like I would simulate, write it down on a piece of paper. And it's a deep question, and I don't know how you would, like, I'm not an experimentalist, so I don't know how you would test that. You have to get down through those layers that we're talking about, and you have to somehow probe what's going on in the processor itself. I don't know if you have any comments or questions.
I do have comments and questions. So the first thing is that this is based on the SYK model. And as I said, S of SYK is Sabir Sachdev. He's an FQXi member. But as far as I understand it, it's not an exact realization of the SYK model. It's sort of an approximation to that. So even though the SYK model would be related to a duality, there have been some comments that this wasn't even a realization of the SYK model as it is theoretically outlined. It's an approximation to that. So that probably, gets rid of the whole option that this has really been created in the quantum computer, because it's only an approximation of it. So we haven't really created a wormhole. But let's imagine that it wasn't an approximation. Let's imagine in the future they actually model this or create an example of what the SYK model predicts for the qubits, and they do that perfectly well. So my first question is then, if this theory has been worked out between quantum theory and a space-time theory, but the space-time theory is in ADS space-time, and we live in DS space-time, are we saying that there is a possibility that this still holds and the qubits do whatever the qubits do on the entanglement side, and a wormhole has been created, but that wormhole is in ADS space, even though we don't live in ADS space? Or are we saying that we're just assuming that because we have this conjecture that relates ADS space to quantum theory, that there is also a corresponding conjecture that people have been trying to work on but haven't really ironed out, but that does relate to our actual universe, and thus we are going to take on faith that a wormhole in our space-time has been created?
So, as good scientists, we should never take anything just on faith. However, Jim Cushing, who was the late Jim Cushing, who was a philosopher of physics, made a very interesting point in one of his books. He goes through the interpretations of quantum mechanics, and he makes the point that in order to decide on the accuracy of a scientific theory, there are two ways to go about doing it. You've got your inductive and deductive. And Cushing makes the point that, at least in quantum mechanics, neither of those independently nor the two of them together is sufficient to decide on a correct, at least in this case we would call it an interpretation, right? So there's this sense, there has to be something other than what we usually use, faith or beauty or something like that, to make a choice about these kinds of things. So in regards to this, first I want to emphasize that all of these things are just models, and that all our models are approximations. Everything is an approximation. Until we have a theory of everything, everything is an approximation that only is valid under certain circumstances. Now, we live in a de Sitter space, but that doesn't mean that there aren't little pockets that we could use that are, approximately anti-de-Sitter, right? I mean, we live on the surface of the planet, and I'm sorry, I hate to burst anyone's bubble, but it's a globe. But, of course, when you look outside, it sure doesn't look that way. If you've ever been to Kansas or places in Australia or other places that are just insanely flat, you'd be like, well, certainly the Earth is flat, right? The point is that I think in this regard, there's certainly an assumption that some of these theories, so like the SYK theory, great theory, but this is an approximation to it. Well, in some sense, the SYK theory is an approximation describing something too. So it just means it's a slightly different take on things. This subtle thing about models, right? So, like, take Newtonian gravity, right? So Newtonian gravity is absolutely correct in its realm of applicability. We rely on Newtonian gravity every single day. Nobody uses relativity to build bridges and cars and buildings. They use Newtonian mechanics. Now, you can actually derive Newtonian mechanics from general relativity. Like, it literally falls right out of general relativity. So all it means is that it's a special case, right? So these theories, these SYK theories and things like that, are all ultimately, every theory, one would assume, if it exists, is a special case of a theory of everything. Like I said, if it exists.
I'm going to keep pushing you.
Okay.
We've got this example here where something has happened with some qubits and a wormhole may or may not have been created as a result because of this duality. I'm going to go back to what I said at the outset about the SYK model being originally developed in the context of condensed matter. And the reason I want to bring that up is because Sabir Sachdev, like I say, I interviewed him fairly recently about this, and he was talking about how he was originally interested in trying to understand more about the origins of high-temperature superconductivity. And he was looking at materials in the lab that could exhibit this, and he found a set of metals called strange metals that have some slightly weird properties, and he was trying to think about the theory behind them to describe their behavior. And he ended up finding, through his theoretical analysis of strange metals, he was finding a lot of resonances with the theory of the behavior of black holes. And he spent a lot of work thinking about strange metals and black holes and the connection between the two. And he was finding this kind of duality. And I think he wasn't even originally aware of the ADS-CFT conjecture at the time. He was made aware of it as it was developed. And he was sort of like, oh, here are more examples of where something that you analyze that's got a quantum behavior, in this case, the superconductivity, has a dual in describing the properties of an object that's really only affected by gravity. So in this case, a black hole. And actually, this ADS-CFT conjecture has been used by, a band of condensed matter theorists to help them do calculations to better understand, what would happen in the lab when they do experiments with their condensed matter system. So real labs, real experimental physicists making materials, doing experiments on those materials and measuring properties of those materials. So my question is now, if a duality exists between strange metals and black holes, and we create a strange metal in the lab that has certain properties that are dual to the properties of black hole, are we saying that a black hole has been created in the lab?
I'm going to answer that with a slightly simplified example. If you know a little bit of physics, you will know that if you look at Newton's universal law of gravitation, the force between two gravitating bodies is G, which is this constant, times the mass of one times the mass of the other divided by the square of the distance between them, right? If you look at the force between two charged particles, it has a similar form. It has a constant, K, and then the charge of one times the charge of the other divided by the square of the distance between them, K, Q1, Q2 over R squared. There has been a lot made about why those two laws look the same. Like, they're both 1 over R squared laws. They have the same number of symbols. They have the same number of inputs, right? Why? Why the heck do they look like that? Why do they look the same? No one really knows. You could postulate that there's some kind of duality there. On the other hand, I've also heard people say, well, any spherically symmetric law will most likely have a 1 over R squared term in it. Maybe it's just because they're both spherically symmetric, and that has really nothing to do with anything deeper than that. So it could be that this ADS-CFT correspondence, duality, whatever, is nothing more than this kind of thing, right? So you have to be very careful. And I'm going to go back to the fact that there is no mathematical proof of this ADS-CFT correspondence. So right now, all we've got is, oh yeah, they look like they act the same. Yeah, well, so does electrostatics and gravity, right? So
now we come to, I know you're sick of this subject now, I can see it, but we're going to come to the sociological sort of aspect of this. And you've spoken about how there's no mathematical proof of this conjecture. I think one of the reasons this really erupted on social media and it really upset a lot of physicists is that this is about something else. This is not exactly about this particular paper or this article, but there is a lot of sort of long-term controversy or resentment about this whole area of study, which is related to string theory, which is related to this ADS CFT conjecture. As I say, a lot of people say ADS is nothing to do with the space-time we live in. There's no proof of it. There's no proof for string theory. There's no mathematical proof of this conjecture. And the way this was being shared around, so there was upset, understandable upset, that maybe it was being promoted as the creation of a wormhole, although I think we've explained that there are subtleties there. It wasn't just that, people were making things up. There are subtleties here about why you might want to make that claim and why maybe you shouldn't make that claim. But that was sort of one level. But it should be said that, from what I saw, and I'm a journalist, so I'm coming at this, I'm biased towards the journalists. I was looking at the publications. I was looking at the headlines. I was looking at the stories. The reporters on these stories were pretty much always kind of the best physics reporter that publication had, right? These were not sort of newbies. These are not people that have never heard of this topic before. They knew their stuff. They were often thinking about it quite deeply, putting a lot of thought into their reporting about it and trying to bring a lot of these nuances out. But there were statements flying around that were more subtle than saying that a wormhole had been created, but they were saying things like, this is evidence for the ADS-CFT conjecture, which I don't think it is. And I think, as we've discussed it isn't. So something did happen. This paper came out in Nature in November. The title was Traversable Wormhole Dynamics on a Quantum Processor. This was a cover story on Nature. It was, it's got a lovely image on the cover, a holographic wormhole. And the press release says this is the first known report of a quantum simulation of a holographic wormhole on a quantum processor. So the press release was a little bit more conservative than perhaps the title of the paper. It was featured with a News and Views article, which was written by Adam Brown and Leonard Susskind, who are FQXi members, and it was called A Holographic Wormhole in a Quantum Computer. And then it was widely reported, across a number of different outlets, some being, specialty physics outlets, some being specialty science outlets, and some being mainstream outlets. What went wrong? Or did anything go wrong? Like I say, there are a few levels of communication. There is the paper, there's the News and Views, there is the press release, and then it goes from the press release to the journalists who then interview the physicists who took part in the study, and they interview other people about it. And sometimes the people who were involved in the study and people commentating can be perhaps a little overly enthusiastic about what has been done. So, where in the chain was there a breakdown? Or was there a breakdown?
So I don't think there's one spot in the chain where there was a breakdown, but I think it's important to understand a few things about how science and the physics community in general operate. So the first thing is to understand Nature as a publication. It's an excellent publication. It's been around for 150 years or whatever. Their publication model is a little bit different than a typical journal. So like, the physical review journals or the Proceedings of the Royal Society or, those kinds of journals are usually run by nonprofits. Nature is a for-profit company, and I don't mean to make light of that, but they want to see flashy headlines. They do undergo peer review, but then the editorial board, Nature likes to drum up some controversy, we'll say, because it's good for the bottom line and it generates excitement. Nature also, because of sort of their model, they have an embargo. So typically, if I publish in Physical Review D or Physical Review A, my paper, most likely people will have already known about it, and the publication is almost like a rubber stamp to some extent, in the sense that it's been on the archive for a while, and anyone who should have seen it has probably seen it. And Nature, they have an embargo where if you publish a paper with them, you're not allowed to talk about it until there's a date where they say, okay, we're going to release this publicly. I don't know if it's the publication date or whatever. The idea behind that is to create buzz around the paper. I know a lot of people who have a really hard time with that. That's not really the way science should be done, or at least some people think that. And so when you have that, that naturally then creates a little bit of hype. And then I think from that point, it also comes down to, we're all human beings. Like, I think people want there to be evidence of a wormhole or something. Like, it captures the imagination. And so people get carried away. And scientists do it all the time. We are in this field because we are excited by it. And I should, by the way, mention to our listeners that, yes, you are a science journalist, but you also have a PhD in physics. So you know your stuff. And I think a lot of these science writers are like that too. We're all in this because it's cool. We like it. It's interesting stuff. Well, we can poo-poo this and say, no, there was no wormhole. The fact is we don't know. We have no idea. So we can't disprove it. And so the imagination runs wild when you get to that point where you can't disprove it. And you get these heavy suggestions that, oh, maybe. But I do think that Nature's publishing model contributed to it. I'm not disrespecting Nature at all. I'm just saying I just think that particular model does lend itself to that.
Okay, well, thank you very much for indulging me there. It came out, all the headlines were there, people got really excited, and then it took such a battering. I mean, it was really painful if you were on social media at that point. It seemed disproportionate, maybe. And this isn't something that's going to go away. So even if we can, like you say, poo-poo this one and say, well, a wormhole wasn't created, there will be more experiments, and this is going to come up again and again. And who knows, maybe at some point it will get on to your list, Ian. But as of now, it hasn't. But but at least we've explained very, very thoroughly why it hasn't.
Yes, and I don't want to downplay the result. I mean, I think the result is still really important. It's good science, good physics. I think it's certainly a step in the right direction. It's good stuff. So, yeah, I don't want to downplay it at all.
So that was a very long discussion of a couple of the highlights of the year that didn't quite make our top 5. On the podcast page, fqxi.org/community/podcast, you can find out more about the Nobel Prize winners Alan S. Spey, John F. Clauser and Anton Zeilinger, and the Breakthrough Prize winners David Deutsch, Peter Shaw, Charlie Bennett and Gilles Brassard. And as promised, I will be linking to George Musser's report on emergence, which delves deeply first into some exciting advances in condensed matter in recent years. So you can read more about Sabir Sachdev's work and others, and the puzzle of high-temperature superconductivity in strange metals. Then George talks about developments in quantum gravity, and his 4th chapter discusses bringing those two seemingly disparate fields together in the SYK model and experiments with wormholes. If you just want a taster of that 60-page report, there's also a shorter article that I wrote for the John Templeton Foundation earlier in the year about the SYK model that touches on these wormhole tests. And of course, there are lots of resources to read more about this particular wormhole paper by Maria Sparopoulou of Caltech and colleagues, published in Nature. In the next edition, we will begin Ian's top 5. Till then, thank you very much, Ian Durham. You can reach me at FQXi on Twitter and Ian at Quantum Moxie. You can also find us on Facebook, Instagram, TikTok, and Pinterest at FQXi Physics, on LinkedIn at FQXi, and on Mastodon at FQXi@sciencemastodon.com. Oh, and of course, there's always the old-fashioned way of emailing us at podcast@fqxi.org. But the best way to reach us is probably on Twitter. Thank you for listening. I've been Zeeya Merali.